In problem 3, we're going to be talking about the likelihood ratio test. And before we get into the actual problem, I'm going to give you some quick motivation over why the likelihood ratio test is something nice to learn and why this problem is helpful. And so the likelihood ratio test, on a very high level, just think of it as a statistical test that is used to compare the goodness of fit for two competing statistical models. Okay, now let's get into the actual question. It says, suppose we observe x is a real number is drawn from one of two distributions, P0 with the PDF of P0 of x, or P1 with the PDF P1 of x. It gives us a possible randomized test, or it tells us that a possible randomized test is a function, phi, which basically maps to the real numbers and returns a value between 0 and 1. It says that phi of x denotes the probability of deciding P1 when observing x. So let me rephrase that for you slightly. We have some function, phi of x. It basically outputs numbers between 0 and 1. And this phi of x is equal to the probability of deciding P1 when observing x. So let me write that down. It's the probability of deciding P1 when observing x. In other words, we're basically saying that we believe that x came from the P1 PDF, the P1 probability distribution, and not the P0 probability distribution. Okay, and so now, if we kind of break this down further, because phi of x is a probability of deciding that P1 is the PDF when observing x, we can say that if phi of x is equal to 1, well, then we know we should always choose P1 as the probability distribution. If phi of x equals 0, well, if the probability of deciding P1 is equal to 0, then that means we always choose P0. Another way to think about it is like a positive versus a negative. Like P1 can be the distribution that represents choosing something to be positive, and P0 can be choosing something to be negative. So let's say like you're trying to detect whether someone has an illness, and P1 is yes, they have an illness, and P0 is like no, they don't have an illness. And so depending on what this phi of x is, you would either choose P1, which is positive, they do have an illness, or P0, which is, or if phi of x is 0, you might always choose P0, which means you think they don't have an illness. Or if phi of x is between 0 and 1, then we randomly choose the distribution. Okay. Now the next part of the problem says the size and power of the test are this and this. And that looks really complicated, so I'm going to try my best to explain what this means. So when we see the size of a test, basically kind of think of it like this. So we have this function phi of x, which tells us the probability of deciding P1 is the probability distribution. And here it's the expectation of choosing P1. You can almost think of it as the expectation of choosing like let's say P1 is the distribution that represents, oh, this person does have an illness, it's positive, versus P0 is, oh, this person doesn't have an illness, it's negative. And so like the probability of deciding P1, given that we're choosing from the probability distribution P0, it's basically like saying that this alpha is equivalent to the probability of a false positive, FP representing false positive. And the reason is if the actual distribution is P0, but here we have phi as a probability of deciding P1, then it's the expectation of the probability of deciding P1 given that the original distribution is P0. And so that's basically saying we chose P1 even though the original distribution is P0. And so this is why this size is equivalent to the probability of a false positive. Now let's look at beta. So the power of a test is described as this beta. And this beta, over here you can see, again, phi of x is the probability of deciding with probability distribution 1. Given we actually got this, I guess, point or got this conclusion from the P1 distribution. And so us deciding that some x came from this phi of x, some like big of x is what I'm talking about. Some big of x came from the P1 distribution. Given that it actually came from a P1 distribution, well, this is the probability of a true positive. So FP is false positive and TP is true positive. Okay. And one more thing is remember the probability or the property that the expectation is equal to the integral of x times f of x, where f of x is the PDF. And so we can basically, later I'll show you all, but we can represent expectations as integrals as well. And that will also be very helpful for us. Okay. Now it says, given this, I think this is the Greek letter for Ida is how they pronounce it. Ida or Ida. So yeah, given Ida is greater than 0, the likelihood ratio test with threshold Ida corresponds to the decision rule below, where the likelihood ratio, this capital lambda of x, is equivalent to the PDF of P1. So like the positive, let's say like the positive versus negative, right? Let's say P1 is the classifying something as positive, P0 is it being negative. It's the probability of P1 of x, the positive, over the probability of the negative distribution. And that's arbitrary, by the way. That doesn't have to be the case, but just for clarity, I'm just pretending that P1 represents like the positive. Like, let's say this person does have an illness and P0 being like a negative, this person doesn't have an illness. And so over here, another way to think about this relation is this phi of n of x is a very specific likelihood ratio test. So all tests, a general test basically outputs some number between 0 and 1, and it's the probability of deciding that the P1 distribution is the distribution that x came from. Now this likelihood ratio test is a very specific test. And in this very specific test, again, we either have 1 or 0, where we have this big lambda of x is greater than eta, or this big lambda of x is less than eta. And what this kind of represents is we're saying that this likelihood ratio test is equal to 1. So the probability of deciding P1 is going to be equal to 1 if the PDF of P1 over the PDF of P0 is greater than some Ida value. And similarly, this likelihood ratio test outputs 0. The probability of deciding P1 is 0 if this fraction right over here, right, this Ida is equivalent to this fraction, if this fraction is less than this Ida value. Okay, and so I'm going to just draw a few more pictures just to kind of help hone in what this entire problem is. And so we have, let's say, two distributions, right? This is like P0, and this is P1. And basically, we have like, let's say P0 is a distribution that makes us indicate, oh, this is probably like a negative, like, oh, you don't have an illness. Or P1 can be like some distribution that says, oh, you do have an illness. And we just defined many different kinds of terminology. So we have false positives, right? False positives, FP. This is also called type 1 error. False positives are type 1 error. And again, false positive, the probability of a false positive is the size. So the size, right over here, it's the probability right here. So this is all kind of in like the same bubble. So we have false positives, which are FP, which is type 1 error. And we also have that the size of phi is equivalent to the expectation of P0 of phi of x. Basically, phi of x is a probability of deciding P1, so this size is the expectation of the probability of deciding P1 given we actually got our value from the P0 distribution. And so this is equal to this size. And you can also see this expectation as equivalent to phi of x times P0 of x. So basically, phi of x is like, again, like over here, the expectation is defined as like x times whatever PDF. And so the expectation here is the value inside that's given to the expectation times the distribution, which is P0. Okay, great. And similarly, we have, here, let me give this more space. You can almost think of this as false negatives. And you might be thinking, wait, didn't we just talk about false positives and true positives? So where's this false negative coming in? I'll explain it a bit. So false negatives are called type 2 error. And you can think of it as, so remember, I guess, power right over here, power is equivalent to the expectation of P1 of 5f. So the probability of deciding P1 given we actually got something from the distribution of P1. So this is the power. And this whole thing is equal to 5x times P0 of x. And so power in itself is actually, oh, and I guess in these integrals you need d of x. Sorry, I forgot d of x. But yeah, anyways, in this power, or not in this power, or yeah, and for power, this is actually like, it represents true positives, right? True positives. And I should say this actually represents false positives. So why did I put this power in the false negative or type 2 error box? Well, if you are thinking about true positives, right, there's really only, like, let's say you're given an x. Something is either, if something is a true positive, what's the only other option it can be? So like if it chooses positive, it's a true positive. So if it chooses negative, it must be a false negative. And so a type 2 error or a false negative is actually represented by 1 minus the power. So a false negative, which I will put over here, a false negative is actually 1 minus this. which is equivalent to 1 minus the expectation of P1 of phi of x. And so this basically false negatives and powers are related to each other, even though power, which is represented by this beta, is the expectation of phi of x given p of 1, where p1, like if you probably the sign p1 given you get from the distribution p1, it is a true positive, right? You think it's from p1 and it actually came from p1, it's a true positive, but the complement of a true positive is a false negative, because if you're given an x, you either have a true positive. If it's not a true positive, it must be a false negative. Those are the only two choices it has, positive or negative. And so power is oftentimes, you will probably more commonly see it as 1 minus the power. 1 minus the power tells you the false negatives, and that is, or the probability of it being a false negative, and that is type 2 error. Okay, and so hopefully this box clarifies it a little bit. So this alpha of phi, again, think of it as false positives. This beta of phi is true positives, and you can think of it as this is P1, and then the original distribution is P0. This is P1, and the original distribution is P1. And as a result of being associated as true positives, the power, 1 minus the power, then is associated with false negatives, which is associated with type 2 error. Okay, I know that was a lot, so if that didn't completely make sense, I recommend you rewatch this little part and internalize what does alpha mean, what does beta mean. But to be very quick about it, again, alpha, think of it as the probability of false positives. Beta, think of it as the probability of true positives. 1 minus beta tells us the probability of the false negatives. Okay, given all of this background, now let's go into the actual question. It says, for fixed alpha is between 0 and 1, show that among all tests with sizes at most alpha, the likelihood ratio test with the size exactly alpha has maximum power. They call this the Neyman-Pearson lemma. And so, again, remember we defined any randomized test as this function phi, which outputs some number between 0 and 1 and tells us the probability of deciding that some x came from the P1 distribution. Then we have this very specific likelihood ratio test that says if P1 of x divided by P0 of x is greater than some item, then we give it to 1. The probability of deciding P1 is 1. Otherwise, the probability of deciding P1 is 0. And we want to show that the likelihood ratio test has maximum power. Power is this, right? So the likelihood ratio test with size exactly alpha has maximizes the probability of the true positives, maximizes power, maximizes this beta. Okay, and so to start, again, I'm going to say we want to show that the likelihood ratio test, we want to show that it has max power, or we want to show, or basically we want to maximize, or we want to show that it maximizes the probability of true positives. And another way to kind of think about that is if it maximizes true powers, if this test actually does that, then this likelihood ratio test, this likelihood ratio test's power must be greater than all the other tests, or all the other tests' power must be less than our likelihood ratio test. And so I'm going to define two variables. phi1 is our likelihood ratio test, LRT, and phi is some arbitrary other test. And essentially we want to show that the power of this is always smaller than the power of that, or the power of the likelihood ratio test is always greater than any other test, so it must have maximum power. One way we can do this is we can show, so this is power, right? Remember, beta is power. So the power of other tests minus the power of our likelihood ratio test, we want to show that this is less than or equal to 0. Because if we show that this is less than or equal to 0, then that means that this guy, our likelihood ratio test, phi of n, it must have maximum power if this whole thing is less than or equal to 0. Because that basically indicates that this is greater than that, which is ultimately what we want. And so if we can show that this is greater than that, or in other words, this whole thing is less than or equal to 0, we get our answer. And so I'm going to start by replacing this power, this beta, with the expectation definition. And so this is equal to the expectation of P1 of phi of x minus the expectation of P1 of phi nx. So this is just plugging in the definition of power. And remember, by the definition of expectation, these expectations are equivalent to these. Oh, I just realized, I'm sorry, I made a mistake here. This should be P1. Okay, and so, yes, so we can basically turn these expectations into integrals. Therefore, we can rewrite this as the integral of phi of x, p of 1x, d of x, minus phi of n of x of p1x d of x. And now what we can do is notice how we define in our likelihood ratio test this lambda of x to be equal to p1 of x divided by p0 of x. Therefore, we can say that p1 of x is equal to this times that by multiplying on both sides by p0 of x. So if we replace this with p0x times our lambda x, and we replace this equivalently with lambda of x times our p0x, because that's how this is defined right over here. This will give us, and I'm going to omit writing the x's to make it faster, but just know that they're actually functions of x. We can rewrite this as integral of, and I'm also going to, actually, should I? Okay, yeah. I'm also going to combine these integrals together by subtracting this from this, because notice how p1 of x is the same, right? So we can kind of take, or yes, this p1 is the same, so this part is also the same, so we can kind of take this out and then combine these, because the only things that are different are phi of x and phi of n of x. And so this is equivalent to phi of x minus phi of n of x, and then we take out the lambda of x times the p0, and then the p0 of x. And then this is all with the dx in the very end. And simplifying that, actually, before we simplify that, I'm going to do something else that's very interesting. Is what I'm going to do is I'm going to replace, let's see, I'm going to replace this with this lambda minus ida plus ida. So this doesn't actually change, right? This is equivalent to that. So I'm going to say this is equivalent to integral of phi minus phi of n times lambda minus ida plus ida p0 d of x. And then I'm going to basically split this integral into two by kind of grouping, imagine grouping, multiplying this thing by that, and then this thing by that, and then splitting it up. And so this whole thing is equivalent to phi minus phi n times lambda minus this p0 d of x plus, and then we still have this, but then now the only thing we have is this n left, and then p0 d of x. And now what I'm going to do is this left part is going to stay the same. Oops, did it paste? There you go. And this right part, I'm going to take out the ida and write it as phi minus phi n p0 d of x. So notice how we started with something like phi minus phi n, or we started with p1s, and now we only have p0s. And so because we made that switch, I can actually turn this into, so everything's being multiplied by ida, and we have phi p0 d of x minus phi n p0 d of x. And that's really nice because this is basically equivalent to ida times, and notice how this looks exactly like that. So it looks exactly like alpha, which is size. So this is going to be alpha phi minus alpha of phi of n, just by the definition of what alpha is. So this whole thing can be basically condensed to that. And essentially what we get is this whole equation is equal to this whole thing copy pasted, and then we have plus ida times alpha phi minus alpha 5n. Okie dokie. And so given this, now we're going to do some analysis. So our original whole goal was to show that this equation, which we ended up by expanding and writing it and turning it into an integral, we want to show that this whole thing is less than or equal to 0. And how I'm going to do that is I'm going to do some casework. I'm going to try to split this integral into many cases and kind of show that through these cases that this whole thing must be positive, essentially. Okie dokie. And so how we are going to do that is we're going to split our cases into the following. If our lambda is greater than ida, then what happens? Well, we know that phi of, so when our lambda is greater than ida, in the likelihood ratio test, our 5n is equal to 1. And we're also told earlier in the question that all tests have size at most alpha, and the likelihood ratio test has size exactly alpha. And so we know that this value must be less than or equal to alpha, and this thing must be exactly equal to alpha. Oops. Yeah, this thing must be exactly equal to alpha. Basically, because we were told that the alphas are fixed, right? So with the alphas fixed, this is basically, this equation is ida times a potentially negative number, right? Because something that's less than or equal to minus something that's equal to alpha is like basically like negative or 0. So we're multiplying ida by a negative or 0 number. So this whole thing is going to be less than or equal to 0. And so this term is less than or equal to 0. And when, in this case, so no matter what, first of all, this other term is less than or equal to 0. And so let's just disregard like this for the rest of it, because this is less than or equal to 0, and so we know that it's helping contribute to us showing this entire thing is less than or equal to 0. So now we just have to show that this thing also helps us indicate that the whole equation is less than or equal to 0. And so when this lambda is greater than ida, what we will see is that, let's see, we have our integral, and we have basically phi minus 1, because this 5n is equal to 1 right now. And then we have lambda minus ida. And because lambda is greater than ida, then this lambda minus ida must be a positive number. And then p0, the PDF is always positive. We have this integral. And so now we have to look at this phi. And basically, remember, in any phi equation, phi represents, or phi, I use them interchangeably, but this like phi or this phi, it outputs some number between 0 and 1. So this phi, this must be less than or equal to 1. And so this whole thing, if some number less than or equal to 1 minus 1 is like, this has to be 0 or negative. Therefore, this whole thing is 0 or negative. And so the 0 or negative number times a positive number times a positive number. So this whole integral must be negative. So therefore, this whole thing must be 0 or negative. And if we have a 0 or negative thing plus a 0 or negative term, then this entire equation, under the circumstances that lambda is greater than ida, this whole thing must be less than or equal to 0. So we've shown that for this case, our lovely integral over here is less than or equal to 0. So that's one case complete. And our second case is, so that's case 1. Case 2 is if our lambda in our integral, so this is, we know for a fact that this term is going to be less than or equal to 0 because of the alphas here. And so we just need to show that this term is also going to be less than or equal to 0. And we have information about lambda in respect to ida. So if lambda is equal to 0, then this entire integral becomes lambda minus ida, where lambda equals ida. So this whole thing becomes 0. And the integral of 0 is 0. So we'll have this integral of 0 plus a negative or 0 number. And so this whole thing will also be less than or equal to 0, which is also good. So that's case 2. And in case 3, if lambda is greater than, I'm so sorry. I think I made a mistake here. I didn't mean for ida to be 0. I meant for ida to be equal to or for lambda to be equal to ida. Oh my god, the Greek terms, yeah. So when ida is equal to, or when lambda is equal to ida, when capital lambda is equal to ida, then this subtraction is equal to 0. And when this subtraction is equal to 0, then we have a 0 integral. And so I should probably write, if lambda is equal to ida, then ida minus lambda is equal to 0, which leads us to this 0 integral. And so that's why this whole thing is less than or equal to 0. Our third condition is when lambda is less than phi. There we go. So when lambda is less than phi, then we have the case that our phi of n is equal to 0. Because if you see here, this is the case that we're looking at. And in that case, what we see is, again, the right part of our integral is already 0, so we're just looking at this left part. And in this left part, it's basically, we basically have the integral of phi minus 0. And since phi is basically always going to be greater than or equal to 0, as it's that test that outputs some number between 0 to 1, this whole thing must be a positive number. And so while that is a positive number, we know that what this is being multiplied by, which is this, lambda minus phi, this is a negative number because lambda is less than phi. And so this is a negative number. And we also have that P0 is the PDF, which is always positive. And then we have d of x. And so positive times negative number times a positive number, this entire integral is going to be less than or equal to 0. And then when we add some other part that's less than or equal to 0, the whole thing is less than or equal to 0. So we've shown the three cases: if lambda is greater than phi, if lambda is equal to phi, and if lambda is less than phi, or not phi, the Greek letters. Y'all, I'm actually brain dead. Okay, if lambda is greater than ida, if lambda is equal to ida, or if lambda is less than ida, all the cases, the integral that we have, this big integral, which we derived from here, it's less than or equal to 0. And so basically we've shown that no matter what our beta, which is our power, this equation holds always. And so we've shown that the power for a likelihood ratio test, which is what this represents, is always going to be greater or equal to the like or the power of any other test. And so therefore we have shown that the we have shown basically the Neyman-Pearson lemma, which is that the likelihood ratio test with size alpha has max power because this equation holds. Okay, that was question 1, or part A of question 3. So like question 1 of question 3. And then now we're going to move on to part B of question 3.